Good morning, and let's continue our discussion about finding for the solution of a first order differential equation. So, our topic for today is a homogeneous or equations involving homogeneous coefficients or having homogeneous coefficients. So, this is actually under the topic variable transformation. So, we have two cases here. The first one, um, as I mentioned earlier, it's homogeneous differential equation or equations with homogeneous coefficients. And the next one is case number two, equations that involves linear coefficients in two variables. Okay, so let's focus first on case number one, equations with homogeneous coefficients. Okay, so let's first understand homogeneous functions. So I have here 5 examples of homogeneous functions. The first 3 examples here, 1, 2, 3, these are homogeneous polynomials. Okay, so it means that these functions are very obvious in terms of its homogeneity or being able to identify whether or not a function is homogeneous. So polynomials are functions that can easily be determined whether or not it is a homogeneous function. So now for homogeneous polynomials, so we can say that a function is homogeneous if the degree in each term are the same, okay? Or if they have the same degree. Now take a look at example number 1, x squared minus 3xy plus 4y squared. Let me just turn on my camera so you can see me. Okay, here. Um, so the first term here is degree 2, since you have x squared. The second term, you have x times y, so you have degree 2 also, so 1 plus 1. And for the last term, you have y squared, so degree 2. So as you can see, each term has degree 2, okay, or it is degree 2. Then, since the entire or the functions have the same degree in each term, then this is a homogeneous polynomial or homogeneous function. Now for the second term, another very obvious function that is homogeneous, since you have degree 3 on the first term, and on the second term you have degree 3 also. Since they are of the same degree, then this given function is homogeneous. And for the example number 3, so you have for the first term x raised to 4 times y. So this is degree 5. And for the second term, you have 7y to the fifth. So take a look at the variable here, y raised to 5. The degree of y is 5. Degree 5 for each terms. Therefore, this is a homogeneous function. Again, so the first 3 examples are polynomials that are homogeneous and very easy to determine whether or not it's homogeneous function. Now, for the last 2 examples here, number 4 and number 5. So these are functions that are not so obvious to be a homogeneous function. So, but they're actually homogeneous functions. So how can you say, or what makes these functions homogeneous? That's the question. Okay, because the first 3 examples, by just looking at the degree in each term and being able to, um, to identify the degree in each term and taking note that the degree are equal in each term. So that's a homogeneous function. But for the last 2 examples, you need to apply the homogeneity of a function. Okay, this formal definition will help us determine whether these functions are homogeneous or to prove that these functions are really homogeneous functions. So the formal definition of homogeneity of a function is states that the function f of x and y is said to be homogeneous of degree k in x and y if and only if the function, okay, of lambda x and lambda y, okay, let me just type that Greek word, okay, lambda, Okay, it's a Greek letter. So this is a symbol of lambda. Lambda. Okay. The function of lambda x and lambda y is equal to lambda raised to k times the given function of x and y, or this is the original function. So as you can see in this definition, we will replace x by lambda x and y by lambda y. And if we can be able to factor out lambda, okay, in the given function, giving us lambda raised to k, then the given function is homogeneous of degree k. Again, in this equation here, that degree, okay, let me just, okay, this k here represents the degree of the given function. Okay, so if, for instance, you can't be able to factor out the lambda, or you can still see lambda in the given function, then that equation is not homogeneous. Okay, clear? Again, the first three examples here are very obvious to be homogeneous functions because you can be able to see the degree in each term. But in these last two examples, we will see by applying this formal definition of homogeneity of a function. Okay, so let's go to the next page to show you, okay, why these functions are homogeneous function. Okay, so determine whether or not the function is homogeneous. If it's homogeneous, state the degree of the function. Okay, again, the given example is the given function is 2y cubed times e raised to y over x minus x raised to 4 over x plus 3y. So again, this is our given function f of x and y. Now, what we will do here is we replace x by lambda x and y by lambda y. So replace those variables here. So you just copy the constant to y cubed. So you replace y by lambda y, it will become lambda cubed times y cubed. And here we have an exponential function. You have the variables y and x there. So y becomes lambda y and x lambda x minus the second term here is you have x raised to 4. And this x will be replaced by lambda x. So it will become lambda raised to 4 times x raised to 4 over here in your denominator. So you have x, it will become lambda x, and copy 3, and then y will be replaced by lambda y. Now the next step is to factor out or to remove lambda in the given or in each term of the given function, or you can be able to factor out. If you can do that, you can be able to factor out lambda, then that is a homogeneous function. And the degree of that lambda will determine the degree of the function. So take a look at the first term here. So you have lambda cube in factored form na rin naman siya. So you have here exponential function e raised to lambda y over lambda x. As you can see, you can be able to cancel lambda, right? So we can be able to remove lambda in here in this term. For the second term, you have lambda raised to 4 times x raised to 4. So in its denominator, so you can see lambda and lambda here. So you can factor out lambda, giving us, okay, this given, okay, term, which is factoring out lambda cube in the first term. So you have 2y cubed times e raised to y over x, which is similar to the first term of the given function. And for the second term, you have, so here, factoring out lambda in your denominator. So lambda raised to 4 divided by lambda will give us lambda cube. Now, so we have this term, which is similar to the one you're given, x raised to 4 over x plus 3y. Now, since you can see lambda cube in each term, this signifies that, okay, the given function in each term are homogeneous functions and they are of the same degree. So since you have lambda cube here and lambda cube in the second term, factoring out lambda cube will give us, the original function multiplied to lambda cube. Okay, so now this means that the given function is homogeneous of degree 3 because of this exponent here in your lambda, degree 3 in x and y. Question for this example? Okay, so that's actually, the process and how you can be able to determine whether a function is homogeneous or not. Okay, now we have the next um, example. So determine if this function x over the square root of x squared plus y squared is homogeneous function. Okay, so we will apply, replace x by lambda x, okay, and y by lambda y. So we just copy the function. So now we are to apply lambda x replacing x, lambda y replacing y. So here in your denominator, so you have x squared, which is lambda squared times x squared, plus for your second term, you have lambda squared y squared. As you can see in your denominator, you can factor out lambda squared in here, right? So you have lambda squared times the quantity x squared plus y squared. Square root of lambda squared is lambda. And then you have here, to remain in your denominator is square root of x squared plus y squared. Now lambda over lambda is what? Equal to 1, right? So you can be able to cancel lambda. Then what happens is that when you say lambda over lambda, it's equal to 1 or lambda raised to 0. Okay, lambda or any number raised to 0 is equal to 1. So we put lambda still here to determine the degree of the given function. Now this is the original function x over the square root of x squared plus y squared. Okay, so it means that this function is a homogeneous function of degree 0. Okay, so just a reminder, for homogeneous functions, the degree is not limited to whole numbers. Okay, so you can have a degree that are negative, you can have a degree that is a fraction or any integer. Okay, again, remember, the degree of homogeneous functions are not limited to whole numbers. It could be an integer, okay, a positive and negative numbers, 0, or a fraction. Okay, now we'll have here an example to show you that, like for this example, so square root of x plus y is a homogeneous function. Okay, but the question is, what is the degree of that function? So if you are to apply lambda, replacing x by lambda x, just picture this out. Okay, lambda x and then plus lambda y, factoring out lambda here. So you have square root of lambda. So let me just get a pen so you can be able to see what I'm talking here. So you have lambda times x plus lambda times y. So factoring out lambda, so you have lambda times x plus y. It's under the square root sign. So it means that this is what? Square root of lambda times square root of x plus y, or this is lambda raised to 1/2 times the square root of x plus y. So as you can see, this is a given function here, and this is, of course, will determine the degree of the given function. So 1/2 is the degree again. So as I mentioned earlier, the degree of a homogeneous function is not limited to whole numbers. It could be a fraction. Okay. Now for example number um, 4. So e raised to x. Is e raised to x a homogeneous function? Is this a homogeneous function? Anyone? Now, if you apply lambda here, so replace x by lambda x, so e raised to lambda x. So can you be able to eliminate lambda there? No, you can't be able to eliminate lambda. So it means that this is not a homogeneous function. Okay. Now for number 5, ln of x minus ln of y. So is this a homogeneous function? Okay, let me just show you. Okay, we'll see. You apply lambda, so replace x by lambda x and replace y by lambda y. Okay, so if you are looking at this form of the logarithmic functions, you can't be able to eliminate lambda, but if you transform this or to write in its equivalent or the property of logarithmic function, you can write here lambda x. Okay, the argument will become lambda x over lambda y. See? So in this case, you can cancel lambda, giving us ln of x over y. So as you can see, there's no lambda in the given function. So what's the degree of the function? So you have lambda raised to 0. Okay, na-cancel yung lambda, right? So it's lambda raised to 0 or equal to 1. Then this equation is actually a homogeneous function degree 0. Okay, so again, it's not limited to whole numbers. It could be an integer negative number or negative fraction. So just like this one, let me just go back here. Let me erase this one. Okay, say for instance, 1 over the square root of x minus y. So this is actually a homogeneous function. Okay, so if you apply lambda here, you can be able to factor out lambda, right? So take a look at this. 1 over the square root of lambda x minus lambda y. So what I'm referring earlier is that you can be able to factor out lambda. So that is x minus y. And here you have, okay, let's put 1 here in the numerator. So factoring out lambda, you have 1 over lambda raised to 1/2 multiplied to the square root of x minus y. So your lambda is in denominator. So you can actually bring this up, giving us lambda. If you put this in your numerator, it will become negative 1/2. Its exponent will become negative 1/2, right? So multiplied to 1 over the square root of x minus y. So as you can see, you have the given function and you have lambda raised to k and k is equal to minus 1/2. It means that that equation is homogeneous of degree negative 1/2. Okay, are we clear here? Again, if you can't be able to remove or to factor out lambda, just like in equations, for example, x squared plus 1. Okay, so there's no, it's not, obviously it's not homogeneous because you have a constant here. You put lambda here, then the lambda will just be in that given function. You can't be able to factor out. So this is not homogeneous. And also, say for instance, in polynomials like x squared plus 2x plus y squared. So here, degree 2, and degree 1. If you put lambda, so you have lambda here, you have lambda squared here, and lambda squared also on the last term. So factoring out lambda, you can still see lambda in the first term and lambda on the last term. So it's not homogeneous. Very obvious for polynomials to determine whether it's homogeneous or not. Okay, so any questions or clarifications for determining functions that are homogeneous? No question? So silence means
Wala
yes.
na.
Now let's move on to Solving homogeneous equations. Okay, so in our theorem, in differential equations, if m, a function of x and y, and n, a function of x and y, are both homogeneous, okay, and of the same degree, the function m over n is homogeneous of degree 0. Okay, so a very clear theorem. Since they are both of the same degree, okay, if you put them in a ratio or a in this format, okay, m over n, then you can be able to cancel out their lambdas if you are, to check its homogeneity. So the degree of that lambda, if it's being canceled in the ratio, it's 0. Now, for homogeneous equations, this is the characteristic of a homogeneous equation. It should be the coefficients m and n are functions that are homogeneous and of the same degree. Okay? Take note, it should be the same degree to this function in the second term. And if you are to put it in ratio, m over n, their degree is 0. Okay? Very clear? Now, so what are the steps? Okay, what is the process in solving homogeneous equations? So let's just recall if the degree of all terms of the ordinary differential equation, so since we're solving first order DE, is a constant or is constant and or the same yung degree nila, the ODE is homogeneous and can be solved using the transformation. So you can either use, okay, put y equal to v times x and also replace its differential dy equals v dx plus x dv. Or you can put x equal to v times y and replace x by dx equals v dy plus y dv. It's differential. Are we clear here? Again, homogeneous differential equations is an equation. A homogeneous differential equation is an equation containing m being homogeneous function n homogeneous function, and they are of the same degree. Okay, so that you can be able to conclude that that equation is a homogeneous equation. Now let's solve the DE. So another reminder, so doing the transformation, it will lead us to a separable DE. Okay, you will see later in this example. Let's solve x squared minus xy plus y squared times dx minus xy dy equal to 0. Now again, we have two types of transformations. So you can either put y equal to vx and replace its differential dy is equal to v dx plus x dv. Or you can use x equal to vy and replace the differential dx by v dy plus y dv. Now, it depends on the convenience in your solution. Take a look at this equation. Again, the first step is to identify whether this equation is homogeneous equation or not. So take a look at the coefficient of dx and dy. So is the coefficient of dx a homogeneous function? X squared minus xy plus y squared. Degree 2, degree 2, degree 2. A polynomial, a homogeneous polynomial, degree 2. So check, it's a homogeneous function. Now let's take a look at the coefficient of dy. X times y, degree 2. So degree 2, they are of the same degree and they are both homogeneous functions. Now if you put that in a ratio, m over n, the degree of the ratio is, of the function now is 0. Then this is a homogeneous differential equation. So basta pare-pareho yung degree nila in each term. So degree 2, 2, 2, 2. So that is a homogeneous differential equation. Now, the question is, what is more appropriate or convenient to use, okay, in a transformation? So we will let y equal to v times x. We will replace y by v times x, and dy, of course, is differential also. So it means that the resulting equation will contain variables v times x instead of y times x. So why did I choose y equal to vx? Okay, take a look at the number of terms, okay, in each term. So dx, you have a function that has three terms, one, two, three. dy, it has only one term. So it means that replacing y equal to vx and also dy equal to these two terms will actually be more convenient to solve. Okay, just imagine if you are to replace x and dx, so you will have a three-term polynomial multiplied to a two-term differential vdx plus or vdy plus ydv. So it will be quite tedious. So I mean, for the convenience of the solution. So that's why I have used y equal to vx, or I have utilized, I've decided to use y equal to vx and replace dy by vdx plus xdv. Clear? Okay, so that I have one term to distribute in the two terms differential. Okay, so now I will replace y by vx and change and also substitute dy equal to vdx plus xdv. Okay, let's go. So x squared, you just copy this one, and then copy x, replace y by v times x. You have here. And then for the last term here on your first term of the equation, y squared will become v times x raised to positive 2. So this is our term here in the equation. So dx, so a variable exponential, so just copy this one, minus x, your y is equal to v times x, so this is v times x, and then dy is equal to v dx plus x dv. So now the next step is, of course, we are to remove the grouping symbol here. So x times vx is vx squared. This becomes v squared x squared. And for this term, x times vx is vx squared. So as you can see, there's a common factor here. So you have x squared. You also have x squared here, x squared, x squared. So we can be able to eliminate x squared by dividing the entire equation by x squared. So the resulting equation is 1 minus v plus v squared times dx minus v times the sum v dx plus x dv. Now, I said earlier that by doing this transformation, it will lead us to a separable differential equation. Okay, so first we ought to arrange this equation. So we group factor by group this one, or distribute dx in each term. So 1 minus v times dx. The second term here will become v squared times dx. And distribute minus v in each term here. So minus v times v dx, you have minus v squared dx. Minus v times the positive x dv, you have minus vx dv. Now you combine like terms. Okay, v squared dx minus v squared dx, you can cancel this one. So you have 1 minus v dx minus v times x dv equal to 0. So this equation now is a separable dE, right? So let's continue again. So this is the last part of our equation, or our solution in the previous page. So we are now going to interchange their positions here to, yeah, so we can factor out negative here. So we have minus the quantity v minus 1. They're just the same. And copy the second term here. So minus v times x dv. As you can see, negative, oh, let's go back to the previous. So you have negative and negative here. You can be able to remove negative by multiplying the entire equation by negative 1. And the next step is to separate the variables. You put v together with dv and x to dx. Okay, so we are to remove v minus 1 here to divide the entire equation by v minus 1. You don't need x here, so you divide both sides by x. That's why your resulting equation, okay, multiplying the entire equation by minus 1, you have positive dx over x. This is the first term. And for your second term, you have by multiplying this term by negative 1 and dividing by x and v minus 1. So you have v dv over v minus 1 equal to 0 times these. So 0 pa rin siya. Okay, a pure function of x, pure function of v equal to 0. So we can now integrate each term. So integral of dx over x, so you have ln of x, integral of v dv over v minus 1. So what we will do here is we divide. Okay, the equivalent of v over v minus 1 is 1 plus 1 over v minus 1. So how did you do this? So here, v divided by v minus 1. So we divide that. So 1 is the quotient. So 1 times v minus 1. So you are to subtract now v minus v, so 0. Minus times minus, you have positive 1. So this is the remainder. It means that v over v minus 1 is equal to 1, the quotient, plus 1 over v minus 1. So now you put the equivalent of this given function here. Okay, now we can integrate this term. So distributing the dv in each term, so you have integral of dv plus integral of dv over v minus 1. So you can now integrate this term, so it's v. Integral of dv over v minus 1 is ln of v minus 1. And of course, to simplify the entire equation, so you put c into this form, ln of c. Now you can put these two terms here into one term, ln of x plus ln of v minus 1 is equivalent to ln of x times v minus 1. Okay, the property of logarithmic function. And then you copy plus v equal to ln of c. Now, to eliminate the ln, you can do the anti-ln, or base here is e. So e raised to ln of x times v minus 1 plus v equals e raised to ln of c. Will be able to remove the logarithmic function in on both sides of the equation. So we have the product x times v minus 1 times, of course, you have e raised to v here equals c. Now, this is not yet the final answer since v is not the original variable in your equation. So you are to bring back the original variable. So recall that we replaced y by v times x. So v is equal to y over x. Now you plug in the value of v here. That's why we have x times the quantity y over x minus 1 times e raised to, the value of v is y over x, so you plug it in here, equals c. Now this part of in this side of the equation, this can be written as, okay, y over x minus x over x, or y minus x over x, and then you cancel x here. That's why your final answer is y minus x times e raised to y over x equals c. Okay, so any question here? Any clarification? Any part that you don't understand? Is this clear?
Yes, sir.
Okay, that's great. So let's proceed to our example number 2. Okay, this example will allow us to utilize the other transformation. Okay, so in the previous example, we put y equal to vx. Now here, we will put x equal to v times y. Now, take a look at this. Okay, x times y dx plus x squared plus y squared times dy equal to 0. So first, check the coefficients of dx and dy if they are homogeneous functions. And after that, check if their degree is the same with the other term. Okay, so dx it has a coefficient x times y, in which the degree is 2. Okay. Now for the second term, dy has a coefficient x squared plus y squared. And if you are to check its degree, so you have degree 2, degree 2. So it means this is a homogeneous equation since the degree in each term is the same. If you put the coefficient in the ratio format, like xy over x squared plus y squared, you will have a degree equal to 0. So it means that, or it just proves that the equation is homogeneous differential equation. Okay, so are we clear here? Now, so why I'm going to choose here x equal to vy. So I said earlier that depending on the convenience in your solution, okay, it's more convenient to use x equal to vy since dx has a one-term coefficient compared to the coefficient of dy, which has two terms. Okay, again, just imagine if you are to replace dy by a two term, so a binomial multiplied to a two term. So it's quite, the FOIL method is quite tedious. So you need um, to use an appropriate or to make your solutions more convenient for you. Okay, but if, for instance, that the coefficients are the same number of terms that you can see in there, like dx has two terms and dy has two terms, so you can, of course, select y equal to vx. Okay, that's one of our uh, uh, one that we can use in our solution if it happens to be uh, containing two terms. Okay, so you can use y equal to vx for uniformity purposes. Okay, but in this case, I'm going to use x equal to v times y. And then I will replace dx by its differential, v dy plus y dv. Now we plug it in here in the given equation. So x will be replaced by v times y, just to copy y. And then dx will be replaced by v dy plus y dv. So this is it. This is the term that I'm referring. So plus x squared will be replaced by v squared times y squared plus y squared, just copy y squared here, and then okay, times dy equal to 0. Now, as you can see, there's no more variable x in the equation. So please take note, please make sure that after doing the substitution, the resulting variables are, there are two variables only that you can see in the equation. Okay, now that we have the variables v and y here, we will now try to combine like terms or to simplify this equation, and then leading us to a separable differential equation. Again, the resulting dE will be a separable differential equation. Okay, so let's continue here. Um, okay, so what did I do here? So let me just get a pen so we can simplify first. So here, y times vy is actually v times y squared. So, and then you copy this term, this part of the term, and you have y squared here, you have y squared also here. If you divide the entire equation by y squared, you can be able to simplify it to v times this term, and of course, v squared plus 1. Okay, and you can see that in the next page. So y squared will be eliminated here. Again, take note, y squared will be canceled, y squared, giving us this resulting equation. So v times v dy plus y dv plus v squared plus 1 times dy equal to 0. Okay, now we will distribute v in each term here. So v times v dy is v squared dy plus vy dv, and then plus distribute dy, so v squared dy plus dy. Then combine like terms, so you have v squared dy and v squared dy, so you have 2v squared dy, and then Factoring out dy, so you have 2v squared plus 1 here, okay, times dy. And then on your first term, so you have vy times dv. And this will now be um, separated, or you can be able to perform separation of variables. Okay, so what you need here is a pure function of v, so you remove y by dividing the entire equation by y. And what you need here is a pure function of y, so you divide both sides by 2v squared plus 1. That is why we have this equation v dv over 2v squared plus 1. And on your second term, you have dy over y equal to 0. Now it's pure function of v, and this term is a pure function of y. Then we integrate each term. Okay, so this is ln. Okay, we can use ln here provided that the numerator is the differential of your denominator. So if you check, if you differentiate 2v squared plus 1, this will give us 4v dv. That's why I have put 4 here and then neutralize. Okay, so I have put 1 over 4 outside or before the integral symbol. That's why I have the result 1/4 ln of 2v squared plus 1. And for your second term, you have the integral of dy over y. That's why it's ln of y. Okay, equal to, supposedly it's c, but we can use c, or we can, transform c to simplify the entire equation. So what I did here is that I put 1/4 so that I can be able to eliminate 1/4 in this term. And I put c to be ln of c, so I can be able to eliminate the logarithmic function later. So multiplying the entire equation by 4 will give me ln of 2v squared plus 1. And for this term, you have 4 ln of y equal to, you can cancel 1/4 here, so you have ln of c. Now, for this side of your equation, for the left-hand side, you can be able to combine them provided that your coefficient here is 1. So you can actually transform this term into ln of y raised to 4. And then you can combine this left side of the equation. So giving us here, okay, so we put this term into this format, ln of y raised to 4. And you can combine them, right? Using the property of logarithmic functions. So ln of 2v squared times y raised to 4 as the argument of the logarithmic function on your left-hand side of the equation. And for the right-hand side, you have to copy ln of c and then anti-ln to remove the logarithmic function, okay? So e raised to ln of this argument is equal to 2v squared plus 1 times y raised to 4. E raised to ln of c is equal to c. Now we were able to eliminate the ln in our equation. Now the next step is, of course, this is not your final answer yet. So you are to recall what you did in the first step. So you replaced x by vy. Now you are to bring back the original variable x. So v here is equal to x over y. Now plug it in here. So you have v squared, right? So it becomes x squared over y squared. Okay, no more v's. So we can simplify this one. Then this 2x squared plus y squared over y squared. And as you can see here, y raised to 4 divided by y squared is equal to y raised to 2, or y squared. So this is now your final answer. 2x squared plus y squared times y squared equal to c. Okay, so any question here?
So,
Yes?
so for the 2v square, when you are, what did you do? Did you return the formula of x square divided by y square?
Which part? 2v squared?
Yeah, yeah,
This one?
yes, sir.
Yes. Okay, so v squared, I replaced, or I substituted what? This one, x over y. So recall that. Remember, let me just get a pen so you can see. Okay, so here, this part, let me just write here. So it's actually x over y raised to 2, right? So this is equivalent to what? X
X square.
squared over y squared. Now what happens is that if you can put them into one fraction, so you can actually replace this as y squared over y squared, which is 1, right? So that you can combine them and then copy that same denominator. So 2x squared plus y squared is your numerator for this fraction, and then you can cancel y squared. Okay, so that's why you have this in your final answer. Okay, clear?
Okay, sir. Yes, sir.
Okay, now I think we're clear here. So we will have another example, I think next meeting. Okay, so we'll continue our discussion with case number 2 next meeting. So I hope you can be able to attend our next meeting, and that is on Thursday. So again, it's not the usual practice, but I will be having a special class this week. So that's on Thursday. You are not required to attend, but if you're available on that time, so please do so. The lecture will be recorded, and after discussing some examples, okay, one more example for homogeneous, and then I will introduce this one, um, case number 2, which will involve linear coefficients in two variables. And then after that, I will be showing you your prelim grade, and the prelim grade will not be finalized yet, so that if you have any clarifications, or if you have to ask something about our previous quiz or the result of your prelim exam, I can be able to make an update or corrections with your quiz if you have any questions before finalizing your prelim grades. So after the lecture on Thursday, we will have a breakout activity. So you will be put into a breakout room, and then I'll be calling your names if you are there, and then show your prelim grade. And then if you have any questions, then we can be able to, or I can be able to explain to you, okay, your prelim grade or your scores in your quiz. Okay, so that's all for today. And I hope to see you on Thursday. So you will be seeing the link of the Zoom meeting here. Let me just show you. Okay, wait for a moment. Uh-huh. Okay, here. So you have actually two sections for this topic: variable transformation. The first one is homogeneous DE. So where you were able to find this link. And for Thursday, I'll be um, posting here the link for our Thursday's meeting. Okay, again, the meeting for Thursday is not required, but if you're available, so please attend our lecture, though it will be recorded. So you can see here the link. So you can also see here the problem set number 6. You will have two problem sets for this week. First one is it involves homogeneous differential equation, and the second one is, of course, this topic, linear coefficients in two variables. Okay, so any more questions, guys?
Sir, ano pong masasabi niyo sa grade namin?
I haven't finished yet, so maybe by Wednesday I can be able to finalize my encoding, and then we will talk about that on Thursday. Okay.
Amen.
Okay. Any other questions? But any question in your so Thursday na lang. So we'll have hopefully we can finish the lecture 30 minutes, and then the remaining 1 hour will be dealing with your concerns. Okay. So let me just before we end this class, let me just have okay, let me just stop the recording.